Now, this is fun thing. Right. So, data analytics. Trying to analyze the data you got for the value you have. Okay? So when that value becomes your data, it's like stock price, right? You look at past stock price, you want to predict tomorrow's stock price. That's so precious. Tomorrow's stock price is so precious. But once tomorrow comes, that becomes just another data point. You can add the data, but it becomes data, right? So you always have to do data comes, make the analysis, get the insight, do something with it. Okay. It's up to you. By the way, you can be proactive about it. This is very important. For this class, if you don't tell me anything, I will just have my top 10 list kind of thing. You know, like top 10 list of probability you need to survive by, top 10 kind of analysis, data mining, this and that. But if you actually have some problems that you have in mind, come to me. You can make a case study out of it. Okay, really help you. Really help you. Now, if not, chances are today, in this class, we talk about numerical data, we talk about data from typical regression problem, we talk about image data, picture of cats and dogs, we start with cats and dogs as a good case studies, learning to pick up cats and dogs. By the way, this something you take for granted. It was very difficult. I was at the cutting edge at Imperial College on artificial neural network. Back then, I can tell you this. Getting a robot to walk on two legs was supposedly one of the uncrackable problems when I was your age. It's very easy to have three-legged robot. Okay? But there's a moment of instability where two-legged robots cannot balance. So now you can. Another problem I remember was, remember the optimal control? It's not the right response, but there's a payout. Well, think of backing up the truck. You know what a trailer truck is? Not like the truck that has a truck here, and there's a head, so there's a joint, right? Backing up that truck into it's very difficult. Human beings do that. Okay? Now, there's no right or wrong in individual movement of the steering, but there's a long-term payout in putting the truck into the silo or whatever, the factory floor. That's reinforcement learning. When I was your age, this was very difficult, not doable, not yet. I think we managed to do things like getting computer to balance. Now it's easy. Well, not easy, but now it's done. So, there's been a lot of advance in the past decades. Right. So, shifting gears. I don't want you to say data analytics is machine learning. Right? If I want you to say anything, data analytics is building some kind of quantitative inference, some kind of quantitative model. It just happens that the tools for building those models nowadays, machine learning tools, are so powerful. Yeah. So, I said, we learning about transportation. Transportation doesn't mean driving a car, it could mean walking. But, because this city is only built for driving, you learn a lot about cars. Okay? So data analytics is not machine learning. And to prove a point, what if data analytics is for you to build a model? What if the model you build is in your head? do that already. Then what's the point of having computers? Well, that's where computer visualization is. When computer turns data into visualization, pictures, graphs, plots, you can build mental models, not mathematical model, not machine learning, not statistical model in your head. But if I give you two things, right? I give you a table of numbers. X and Y, 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 X and Y. And I ask you to build a mental model, not mathematical model, mental model of Y as a function of X. Very hard. But if I take the same numbers and I plot it, and you notice that it's possible straight line, what happens? You right away, you know that there's a linear relationship, right? So when I say building a data analytics, it's about building models. There's a big chunk of data analytics that's devoted to visualization. Because what it does allows you to build mental models, picking up patterns. Better in higher dimension. That's another thing as well, right? So seeing tables of numbers doesn't give you any intuition. Seeing a graph does. Seeing a graph in higher dimension, well, it's a bit hard, so maybe I can work with that. There's some tools that, so all this visualization, these are harmful things. It's not giving you the model in the sense of X gives you Y, because that's going to be good in the end. But you can do a better job, right? If you see a plot, that's where visualization comes in. So that's a good example of what an instance where data analytics doesn't involve machine learning whatsoever. Right? Just visualization, but very good visualization. So you learn about it. Now we're going to talk about machine learning. Before I do that, I have to tell you that you are supposed to get a mathematical license. For some reason, there's some technical issue why the license was assigned to my summer school student and can't transfer that to you. I don't know. Okay. You may have heard of Python. Well, to be done, mathematics is much better, much more powerful. The reason it's not everywhere is because it's not free, one thing. It's not open. Just like any system, if you have a closed system, it may be pretty, it may be beautiful, but it's only as good as the ecosystem. Python is much better than Mathematica in that sense, because it's open license, nobody has to buy anything. You can be a biologist and you come up with some algorithm in biology, you try to R as another language. So Python and R are the same thing. General purpose language, very open, inherently not powerful, but it's powerful in the same way English language is powerful. Because, the more Indian words and Greek words in English, okay? So it's an open platform, that's what R is. But because it's a generic language, it's well, to me, I think it's a little bit concept. With Mathematica, it's designed. And it's designed for a job. And the job that they designed it for is much harder than the job you have. The job that Mathematica is designed for is to solve physics problems. Much more difficult than what we deal with. So a lot of things that we are going to deal with have been encapsulated in a very easy plug and play kind of thing. In other words, if you're going to do this machine learning, and that's remember I told you that you're going to be doing some coding, you're going to have an opportunity to do real life coding in Python. Get the data, put it in the standard form, standard structure, pull, group by, make this pull the scikit-learn or TensorFlow library and make a build a model, right? Because this is so routine. Mathematica does have a high level description. So we say something like, look at this data set, abstract. And what it would do is search over a small space of models. not comprehensive, not comprehensive. So it would be like a good starting place. And it's something that I would teach because, again, some of you are not going to be in the applied digital intelligence track. If you're in the applied digital intelligence track, you have to learn Python simply because the world speaks Python. If you graduate, you don't speak Python, it's like you don't speak English. But Mathematica is something very quick, very high level, very powerful, and it does there are certain set of capabilities that no amount of library in Python can achieve. But not all of that is relevant to our cases or mathematics. But at the very least, the visualization, that's what I'm saying. The visualization tools in mathematics is it's much easier. I don't know if you have some experience with Python programming, math calculation, and so forth. It's a very clumsy way to do it. Okay, no. I have my own staff who's done this for 10 years, and to him, it's just that quick. But it's boilerplate. You have to write. Basically, you have to write 5 for every one line I write. But they're very quick. They're very quick. They can just copy and paste. And they've done this 1,000 times. So yes, my staff can write 10 lines of Python faster than I can write 2 lines of mathematics. But that's because my staff has been writing Python for 10 years.
And it's very much customizable. So like if you can change anything, everything, and you can leverage CD, you can leverage Portland. Like
Yeah. Back end, you can do that. Yeah. But it's definitely not a high level language. There's a lot of what's called boilerplate. Boilerplate means I want to get from here to there. Instead of saying go from here to there, there's always a step that involves walk, lift, and you just copy paste, do it.
And like with the vocabulary, it's like it's
that's what trying to do. They try to do that. In fact, Jupyter, you know that, right? Jupyter, the way you write the script is copied from mathematics, simply because they want to do that kind of higher level. So yeah, Python is not lying there, it's evolving. Python tried to get higher level and higher level. And when Python came out, I think in the 70s, some of my friend from Imperial was really into Python. It was very clumsy. And after a while, they looked at Mathematica in the kernel script programming, and somebody said, hey, let's do this for Python. And they have Jupyter. So they copied that from Mathematica kernel. So it becomes more high level, and it's more interactive. So yeah, Python is, I'm not saying Python today is Python 20 years ago, no. But it's still a very base language. Very base language. And it had to do analytical. Now, my job is different from your job. I'm not just a data scientist, I'm a financial engineer. So I need to do something like analytical differentiation of heuristic Python. If I were to do this in Python, it's always numerical. Can't do analytical. Mathematica, because it was created for physics, to do equations, I can actually write differential equations and solve it analytically. That's amazing. That's something that, amazing. You can never do that, but that's not that relevant for you here because you're not financial engineer. But I did that in my job. I had to do financial engineering. Financial engineering is like you have financial things like stock, right? With Wiggle, and then you create a contract on that depends on that functionality. But because this is Wiggle, this is also Wiggle. How do I price this thing relative to that thing without what's called arbitrage, meaning giving my money away? It's very mathematical. It takes this kind of stochastic version of differentiation. That's another thing. The interpreter would not be able to do stochastic differentiation. So translate from this to this. They get some solution. So a lot, now having said that, a lot of the time when we do things like data mining, predicting behavior, my staff is using Python. Why? Because even though they have to write a lot more code in the beginning, when they port it to the application, they can link that to deployment. Mathematica doesn't do deployment well because it doesn't talk to anybody. It's very prissy kind of language, but it's extremely powerful. Because it has more probability distribution than R. R 10 years ago was the language for probability distribution. Now it has less. Now it can't do fancy distribution. Anyway, so that's sort of like beside the point. So to this class, you have the mathematical tool that will help you with A, visualization, B, interactive programming. So you don't have to do a lot of widget, which you can do with Matplotlib, but it's very, very painful. Okay. So let's talk about machine learning. And that's the last thing we talk about. Hopefully, you will have my next week Mathematica installed, and I'll teach the primitives. And right. So machine. What is a machine? Let's define it in a very simple way. Machine is something that performs something. The idea with machine learning is that it's the machine that has two tasks. That's it. Okay? If I have a drilling machine, it drills. Okay? If I have a calculator, it add, subtract, multiply, divide. Okay. A machine learning has two tasks. The first task is to learn the problem. It's only once it's done the first task, then it does the second task, which is make predictions, right? Which is what, so if you think about it, wait a minute, it's not very good, right? Because it can't do anything by itself. It's got to learn first before it does anything. Well, that's human beings, right? Animals can immediately do things right away. They don't have to learn, right? On day one, giraffes start walking and running, right? So they don't have to learn. They function right away. No learning, because it's all instinctive. But that only gets them so far. Okay? So learning happens at evolutionary scale. Meaning for giraffe to learn new capability, it has to evolve genetically. Yeah. On the other hand, squid. Squids have a learning capability during their life. So on day one, they cannot open the jar, but they can learn to open the jar. So while they're learning, they're not being fed. So there's a period when they're useless. But once they are able to open a jar, they can eat food that no other animals can. Same thing with human beings. We are powerful because we are useless for 20 years of our life. Think about it. You haven't done anything positive to the world. You just consume for 20 years. You haven't produced anything. You just consume. Consume food, consume attention, consume education. You haven't made a single thing, right? That's why you're powerful. You're capable of producing things a lot more than if you quit school at age 3. Right? So there's a delay period where you just learn, you don't do anything. That's the technical. Machine learning is only the answer. It's only the answer if the task has not been achieved. If the task is multiplying 2 by 2, I use a calculator. Okay. Now think. Okay, this is no exaggeration. This is doable. I have a calculator. Multiply any two numbers. I built it in a chip spreadsheet. I can also build a deep learning machine, AI, that looks at 2 numbers and the third number I see 2, 2, I see 4, 2, 3, I see 6, I see 7, 8, 56. I can see a million of them, and I can accurately multiply 7 by 32 without having seen that combination. Because continuity in mathematics. So I can do that. Am I going to do that? So what am I going to do? Am I going to buy a calculator that costs 200 baht? Or am I going to build deep learning engine and supply with simulated tables of number and have it learn multiplication by heart? In the hope that one day I'm going to do 7 multiplied by 22 without it having seen it before accurately. I can do that. That's a marvel, by the way. That's doable. That's doable. Nobody does that in practice. Okay? So why would you use machine learning? It's because you have some task that is not already achievable by a built machine. So machine learning is only used when you don't have a built machine to do the job. Now, what is statistical modeling? Statistical modeling is the same thing as a built machine, except it's built by mathematics. That is the biggest distinction between statistical modeling and machine learning. Statistical modeling is pre-built. It's not built by you, it's built by mathematicians over 500 years. Okay? But it's built. You can look up. It's a big book, by the way. It's always looked up in America. And its family. If your job is to estimate distribution of something and it fits in the book, you would not use machine learning, you use statistical model. Statistical model is a built machine. Machine learning is a machine that you build it learn first. And until it learns, it's completely useless. And in application, it's always a balance between how much it costs to improve learning. Because learning is not a yes-no thing. Yeah? You can actually do this. You can actually compromise. You can build a good machine learning algorithm. It takes a lot of time. It takes a video card, this thing. But you take 10 of these, run for 8 hours. You have another algorithm that maybe just takes one of these and run for 5 minutes. And one is a lot more accurate than the other. But maybe that's not what you need. Also, it's not just learning time, it's also latency of response. We talk about the velocity. I'm not going to go to that much more than this, but in velocity, that means give me X and give prediction Y. Well, once the machine takes a long time to learn, some algorithms also take a long time to output, right? So sometimes you don't want the best, more accurate. If it takes a long time to learn, it takes an expensive thing to do. Okay? So machine learning, now, with so there's a little bit of pick and choose. Statistics do that too. You don't know this, but actually do, yeah. Statistician, professional statistician, they can choose this distribution, they can choose this distribution. This one's more accurate, but this one is easier to choose. So there's also practical trade-off, even in mathematics, right? You can say absolutely who's better with respect to this data set, but who is better for this job? Still a little bit of engineering. Yeah, you think of it, it's an engineering trade-off, computation time, blah, blah, blah. But in statistics, usually it's not much of a debate. It's not much of a consideration. You pretty much, yeah, you just pick this one. But machine learning, there's a lot of leeway. There's a lot of leeway. Like when I take on a project, I have different level of accuracy expectation, speed expectation. So sometimes I actually go for a simpler, dumber model because it's easier to compute and it's also easier to look inside. That's not an issue we'll talk about later. It's called model transparency. Yeah. Now, so the thing is, again, by the way, in real life, this is the expensive one, the learning task. That's the expensive one. And performing tasks tend to be what's called recall mode. Now, so that's what the machine does. Machine does. Now, what do I mean by learning? Learning involves two things: the action and the object. The action and the object. Okay? The object is the basis of learning. What do you base your learning on? Okay? You can base your learning on books, like human learning, right? For machine learning, I'm going to say a lot of times your learning is based on empirical data. Okay? I just put that there for completeness, but I might as well say you learn from data. Okay? This is your learning resource. You learn from empirical evidence. There are times when you learn from simulation environment. There are times when you learn from passive evaluation, some kind of, and this is, you know, like a deep mind that plays Atari. Yeah. Well, that is passive evaluation. The Atari game is passive evaluation. It's not a part. Yeah. On the other hand, AlphaGo, when it looks at a whole bunch of people playing Go, that's a part of it. Because it's not learning the principle of the game, it's looking at people playing games. Yeah, so it's part of it. Simulated environment, sometimes you have to kind of deep fake kind of thing. But anyway, I don't want you to spend too much time on that, but basically empirical evidence is the thing. It's what you're responsible for. And for good reason. For good reason. Most application cases involve mapping this. So you can think of well, let's talk regression equation. You can learn one regression equation, right? But every time you go to a new problem, you get a new data set, right? So one technique, so many data sets. It's a little bit like that. Machine learning is like a tool bag. You have technique, but what changes from day to day? Yeah, your choice of model for the tool bag changes. But what changes more than that? The data you get. That's empirical. So that's why if you use machine learning in data analytics, the things that is new, the technique may not be new, the problem may not be new, but every time, I guarantee you, you walk through a new project, what's new is data. Okay? It could be the data set that's similar to what you worked on before, but it has a different feature. Okay? And we talk about transfer learning in that context later. But the point is, that's it. That's it. Machine learns from empirical evidence. And that is the reason why we study machine learning in data analytics. Because data, okay, data is not just a problem, data is the resource. Right? Remember? Data is nothing if you can't make insight. If you take data and you visualize it, and you can make a mental map and you make insight, good for you. Good for you. If you can't do that, you take data, you give it to a machine learning engine, it learns this. This is your empirical evidence. This is what builds machine learning. Okay? So, like I said, this is the most expensive part of a machine learning algorithm is the learning part. The prediction part is easy. Then it's like it takes years to learn cloud formation from brain. Okay, but it takes you just a second. You look at the cloud. Wow, this is gonna be. So this kind of from X to Y is easy. It's the F that you have to create. That's the problem. Okay. Now, algorithm-wise, there's always, and this thing is, what did I call? Sometimes you do this thing called bias and variance. Yeah. It's always like this. You don't learn from the past, You don't know anything about the future. But the past is not exactly the same thing as the future. So how much of the past did you learn? Okay? The future follows the past. The future trend follows the past trend, but it's never exact. So where do you cut off? Think of a wave. Okay? Think of a tiny wave. Think of a tiny. Okay? Let's say, I'm just going to give you the answer. The answer is, on a day-to-day, this big wave is that. But the little wave, that's random. If I told you this, you know what to do. You ignore all the little variations, you go to the big variation. That's it, that's done. That's the difference between learning and learning too much. Learning, you want to learn this, but you don't want to learn this same thing. Okay? The point is, algorithmically, it's very difficult. Stop. Yeah, it's like during class, don't walk out. Fine. Okay, there's fire. You don't walk out. But you told me not to walk out. Well, it's not exactly the same thing. There's always a generalization limit. Okay? And that common sense tells you is what you should do. You should learn the trend, the big trend, not the tiny variation, but quantitatively. The computer doesn't know what tiny is big. It works in any kind of dimension, any kind of precision you like. Okay, so this is very hard. So you have to avoid overfitting, avoid variance fitting, and all kind of stuff. And there's now this is slightly different from. This is where it gets murky, and you have a lot of art to it. Whereas it's statistics, because it's constructed from mathematical assumptions, there's a very precise way of describing how you fit the model. And so you don't have to worry with this kind of issue. Okay? So, yeah, machine learning is more powerful, but it can get too powerful. It can learn past. You know what I mean? Too many details about the past. That doesn't repeat. So if you make that assumption, you're going to make error because the past doesn't repeat. With statistics, because you base your analysis on 500 functions that mathematicians came up with, if it doesn't fit, then you make an error. So there's always a trade-off. It's never clean cut. That's why I tell my staff, my team, don't go for techniques that you like. Okay? There's always two people. You go to a company, fine. They always want the simplest technique that works because they can understand it and they can tell you what. Yeah. You go to your team who's a fresh Ph.D. They always want to go for the more complicated, high-tech, cutting-edge frontier. That's the first thing they go to. Because this thing came out in 2021. Okay? And 2 years ago, they didn't have this algorithm. This algorithm gave 2020. They got to use it. Well, both of those people. I always tell my team, don't go for easy because you're stupid. Don't go for hard because you're unsure. Okay? Go for everything. And let the experiment tell you. And that's been the thing of my consultation work. Now, occasionally you have something like this. Simple model, complicated model, have similar results. In that case, I will deliver the simple model because clients always like simple. But never go for simple just because it's simple. Like there's a good saying by Albert Einstein. In theoretical development, go for the more elegant or the simplest but no simpler. In other words, if you go for simple, just for simple sake, you don't get good physics. Right? So, yeah, there's always a trade-off, and this is something that it's almost impossible to replicate in a classroom. But I can show you, like, theoretically, for example, there's this thing called learning curve. Okay. This is the head of today's lecture. Let's say this is an error. Okay, this is an error. Ooh, it's going down. Yeah. So you keep the model has to learn anything, the model has to learn everything. Okay. Then you throw a curveball and say, hey, try to make predictions on something you haven't seen. Exactly. Now, theoretically, in fact, I would say that means that this thing is learning too much. So you should stop here. Okay. By the way, this is in a textbook, machine learning textbook, you always see this line. Here's what happened in real life. Where are you going to stop? It's not always that obvious. But in classroom, I can make up stylized. But there's a lot more art than you think. What do I mean by art? I don't mean because science doesn't give you the answer, you can show something that looks nice. That's not what I mean. Okay, I don't mean by art in precision. I don't mean by that. When I say art, what I mean is that there are more than one criteria. Not just accuracy, not just computation time, not just ease of explanation. All this has to be done. Every criteria is precise, but the balance is up to you. That's what the art is. So there's always art in data science. Okay. But you have to do the science first, right? You can't just start with the art. Now, and this I talked already earlier about a difference of instead of talking about machine first, let's talk about learning first, and we'll talk about the supervised and supervised. Okay. This thing I'm not going to cover. This is quantum computing. I plan, I think, to teach open the course in quantum computing. Hopefully, in maybe a year or two for my son. Anyway, it's not relevant for learning because all the machine learning is done on it's called one. All the computers in the world is online. So. Okay. Finally, I have before I go, I just want to teach you a little bit of context. Machine learning and AI. In fact, there's slides I'm not going to open up for reading audio. But you always hear this thing about machine learning and AI, and it's always interchangeable sort of thing. Okay. Well, first of all, it's not. Second of all, this is the problem with English language is that one word can mean a few things, and they're not usually exclusive. So English is not additive language in terms of vocabulary. Some language is additive. You say this, you add, modify it. English has come from the whole word, but this word covers this concept. The other word covers the other concept, and they kind of overlap. Sometimes the choice, the synonym, is what matters. Well, especially with the word intelligence, there are actually 3 words here. Intelligence. Okay, what's artificial intelligence? What's intelligence? What's intelligence?
But so like there's no better definition.
No, there is.
No, there is.
There is. There is. There is. Yes, there is. Artificial intelligence just means something artificial in the machine. Artificial intelligence doesn't mean anything. In fact, if I build a computer, a robot companion, that is dumb as rock. I mean, stupid. But, talk like a human being. Even AI. For passing a story. So, artificial in that sense is anything that's not human, mimics human. Enough to fool a human. That's it. That's it. A Turing test classically means, you said the line, right? This is really interesting because that's it, the business line. The Turing test is you sit in a room, you send a message of this paper, you get a response back. And based on the meaning of the change, you can't tell if the other person is a computer or machine as a Turing test. Okay? Well, today, you've got AI that does that. Chatbot. Right? Now, you can probably tell that it's a chatbot because it's giving you too polite an answer. I hate your product. I understand you have frustration. You will try to do our best. Real human being would say that. so something like that. But the point is, if it carries on human behavior, that's called artificial intelligence. Now, I can ask that chatbot, what should I invest in? Okay? And that chatbot can give you the dumbest answer or by Dogecoin. That's not an intelligent answer. That's intelligent. Because intelligence doesn't mean intelligent. It just means human. Like enough to fool human to an extent. So passing a Turing test, what is? What is? That's it. That's the definition of artificial intelligence. And by all accounts, we passed that since 2005.
That's what I meant. So, like the term has evolved. Like it doesn't
Yeah. We talked about intelligence. So we're going to a different meaning of intelligence. Okay.
No, yeah, of course, human cognition.
No. We're not talking about human cognition. We are not saying what is human intelligence. We are saying, can we get a computer to mimic human? That's it. That's all. That's all. And again, that chatbot will give you the dumbest answer. Okay? What's the best way to spend an afternoon? Oh, we'll jump off a cliff. I mean, human beings, some human beings do that, right? They're not very expensive, okay? But it's human life. That's good enough. That's good enough. So human artificial intelligence in that sense just means that. This is why in some, like in my life, there's like a 5 AI class that teach about how to program chatbot. So that's useful. That's useful. That's useful. So that's artificial intelligence in that original meaning. Okay. Now, let's go for 2 more. What else? What other meanings? I already gave you the answer. Business intelligence. Well, this one you may not be familiar with, but this is another meaning of intelligence. This intelligence doesn't mean capability. Okay? That chatbot is a capability, right? It doesn't have to give you answers yet, but ask questions, it has capability to answer. Capability. Intelligence here means information in the sense that it is expensive, hard to come by, overt, precious information. What do you think of? Military intelligence. So business intelligence is exactly the same sense of intelligence. It's not capability, it's piece of information.
Inside
Do you counter something? In military intelligence, you want to know what your enemies are doing. And that information is secret, hard to come by. Moreover, once you got it, you don't say you got it. Because once you got it and you say you got it, you destroy it. Okay? There's a very famous story that Churchill, because at Bletchley Park, they cracked the Enigma code. So they know what the German was gonna bomb. This is Churchill knew it. So he could send Spitfire to cover that area. But if he did that, the German would know, hey, Churchill knows. So the code is broken. We have to get a new code. Churchill had to not say anything and let that deliver move on. Yeah, because that's military intelligence. You got it, you can't really say you got it. Once you got it, and if you say you got it, you destroy it because that Enigma code will be broken the next day. Or it will be infused and they will set it. The German were a little bit lazy that they started saying sentence of every day. So, you know, there reason why it was cracked. Some of it was human error or human carelessness. You know, like I'm supposed to send a secret message. Like every day I start with good morning. So, you know, right away allows you to say good morning to be cracked. Once you crack good morning, so this is the meaning, second meaning of intelligence. Business intelligence is a little bit like that. So sometimes you see a course of this, it should be about it. Now, in business intelligence, your counterparty is not just the enemy, but it's also the customer, right? What else? Employees, exactly. Yeah, they work for you, but they are your counterpart because you work for them, they are happy or not. Right? Now, it may not have that information sensitivity, like if I knew you're not happy about dirty toilet and I clean the toilet, the worker is gonna say, oh, you know my secret. No, they're gonna be happy. So it's not sensitive in that sense. But yeah, what makes the worker happy or not happy, and why would they work for us, and why would they work for the competitor or quit? Okay, that's very important. So you are what else? Your stockholders, your shareholders, right? Because you have to make them happy, and they can just say, I want more. But you know, there's only so many ways you can say even more profit, right? So all this is kind of like intelligence on it's sort of the Sun Tzu Chinese way of war kind of thing, you know your enemy. Except it's not just enemy, it's science. So intelligence in this case is people. Finally, there's intelligence in computational intelligence. This is what I mean by combine those points. So those findings. So intelligent solutions. Solutions that are intelligent, but human beings not come up with it. You use computers to come up with it. Now, you may be able to describe the properties of a good solution. That's easy. That's what you want, right? So the good solution is I want to be able to fill ATM machine with cash before it runs out, but not too often because it costs me money to drive, but not too little because when the cash machine runs out, it gets mad at me and put it back. That's why I can describe it. What's the solution? Right? Well, it turns out this is a very mathematical problem. There's this thing called, you know, I don't know if you heard the traveling salesman problem. It's a hypothetical. The story is you are a salesman. You have to go to the city, right? And because between cities, it takes a car to drive, costs you money to gas. So obviously, if the cities are arranged in a circle, it's obvious. But if it's not, how do you do this? Now, if there are about 5 cities, you can do it like this. If there are about 30 cities, 30 cities possible? I don't know. Let's do the calculation. Right now, there's like you know, what's the maximum number of cities that we solve into? Let's say it's 50 cities. Okay? If you got 50 cities, it takes a computer, supercomputer, the age of universe. It's that difficult. Okay? So an intelligent solution in that case will not be perfect. Because with the fact that, you know, I think maybe 100 cities, but let's just say it's 100 cities. Okay, if I have 100 cities to visit, the combination of going to this city to that city, okay, from the first city to the other 99 cities, to the other 98 cities, to the other, the combination there for the computer to try all of that, even if it takes microseconds per calculation, it will take it 8 years. This is what's called combinatorial explosion. I'll tell you what's funny. This is something done. You guys want to play a card? Yeah. You know that in the history of humanity, there's never been two data cards that exactly ordered. Because 52 times 51 times 15 times 49 times, if the combination blows up really quickly. Blows up quickly. So most likely it's like no place. In the history of humanity, there's been no data card that are exactly the same. Okay? We're not can do this in but this is another easy thing that Python cannot do. That combination. So there has to be that many parts. We even have more than, because this is 52 times 51. Right. So back to our problem. This here means I'm looking at solution that is good. That's good. Okay. So let me go to here. Traveling salesman. Let's see if I got something for it. Yeah, traveling salesman. Find it the shortest distance salesman. By the way, your TA has given a little tablet or player. If you download that, you can play this. You can't write because you don't have a full license. Again, Mathematica is very precision, very stingy when it comes to license. But yeah, you can download and play with this. So yeah, download to desktop and play with it and blah blah blah. There's so many traveling salesman problems. Yeah, so get this thing. So all this is very, very complicated. So that's not the point. The point is that there are problems that you don't get the best solution. It's not like in high school, you have the maximization, right? Maximize minus x minus 1 squared. You know that it's going to look like this, so this is the highest point, right? Here you don't know. It depends on whatever configuration. So the combinatorial explosion is what stops you from getting the best solution. The best solution. So you're now down to good solution. Good solution that at least is better than human. So in this case, it still has artificial intelligence. Because it's not trying to mimic human beings. It's saying at this point, because the combination is so large, human beings not do it. The intelligent thing about human being is we come up with an algorithm, but the computer does the work. Okay? And there are two aspects of scale that we can't use it. Obviously, this is one, right? The number of cities, the number of complications. The other one, obviously, is dimension. Like I told you, if I put male and female height, and I put in 2 dimensions, I can cluster you guys. But if I want to cluster country has GDP, country has mortality index, COVID rate. By the way, we did this. I'll just show you a printout really quickly. So this is a paper. This is actually my kid in high schools. I helped him with this, but it's his project. But this is in Mathematica. You download from COVID, and then you cluster countries, something like that. So you can cluster. In this case, it's not cluster, and the task is dealing by country. Yeah, but you can do cluster as well. So this is grouped by country, but you can do automatic clustering into groups, and we separate into this group Thailand here somewhere, and blah blah blah. So this is high dimensional clustering. Yeah. Again, it's very easy to write in mathematics. High school kids can do it. Okay, so this is kind of like a clustering by multi-dimension. Let me see what the variables are. Variables are like, where's the variable list? Should be here somewhere. That's a list of variable. Oh yeah, is this the guy? Is this guy? Total death per million, population density, cardiovascular death rate, diabetes, prevalence, masturbate, the thousand. So this is different dimensions, but this is visualizing by continent. But if I say, I don't care where you are, I don't care where you are. I want to cluster by similarity in 11 dimensions. How would I do that? Yeah, if it's 2 dimensions, I can do it. If it's 11 dimensions, you write a code for it. Yeah. In Python, you go to scikit-learn, k-means, something like that. Here you just say find cluster, and then generate appropriate stuff. But not this one, the other one. This here. Yeah. So this is, yeah, see, same dimension, but it's a grouping by country, grouped by characteristics. They're actually, a different color, big group here in yellow. That the blue group, that's pretty good. That's vaccinated people and not doing that's a good country to do. Okay, so this is automatic. Now, what does it mean? This is intelligent in the sense that we couldn't do it. Yeah, because we run out of paper. We run out of time, run out of paper, we run out of imagination. We can't visualize high dimension. So this is the third meaning of intelligence, computational intelligence. Computational intelligence, well, that's, by the way, that's my Ph.D. There are 3 sub-brands in computational intelligence. One is like trying to find out what real intelligence, so this will be similar to what you were talking about, solving human computation problems. Yeah, that's part of one branch of computational intelligence. The other branch of computational intelligence is about trying to find optimization using evolutionary algorithms or something like that. The other one is logic. Anyway, it's neither here nor there. The point is, that's the meaning. So now, because this is about finding better solutions. If the solution found is using neural network, okay, let me tell you what the history looks like. History looks like this. People want to mimic human intelligence or human behavior. Yeah. We just say that human is intelligent because we like intelligence. Yeah. It could be called artificial human mimicry. Yeah. Artificial human intelligence. So we want to mimic human intelligence. How intelligent are we? Depends on how our brains work. So they look at how human brains work. They can't do that very well because they look at cat brains. Yeah, assuming cats are mammals, humans are just more bigger cats or something like that. This kind of thing. They did this in the 50s. So basically try to model what cat's brains are like. And by inference, cat brain can be attached to like human being's brain. So they build computer model that mimics that. So this is not about building a model that represents input output. This is about the function that looks like biological behavior. What they found out in cats or in any kind of neuron that you get signals from the neuron into the dendrite of the neuron. Basically, just kind of moves. And if you add up all this, and you add up so much electrical potential, this neuron itself will get excited. And in turn, it will send a signal that will get excited. I don't know. So this function is non-linear. In other words, it's not like you get excited. It's like if I scratch you, you get annoyed. I scratch you more, you get annoyed more. That's linear, right? But sigmoid is a little bit like I scratch you now, you don't care. I scratch you, all of a sudden you get really upset. So it's kind of like a 0-1. It's a threshold to overcome. Okay? That behavior they got from cats and frogs and humans, whatever. So they create computer that does that function. Yeah. That function, by the way, is called sigmoid function. Let me just show you 1 second. Take 1 second. New notebook. Logistic sigmoid A from let's call it sig S for S signal sig S from minus maybe for some reason. There. Okay. Like I said, I expect you a little bit. You don't care, you care. All of a sudden you get excited. Well, this is like adding the complication. So obviously this has a shape. So let's say 3D. Okay, so obviously this is not dramatic enough. So let's you can see that based on the another parameter we can call it tends to like smoothen. So even though you don't have a linear response, you can have sudden response or not so sudden. That's what happens in a human brain. And that's a single neuron. Okay? So you can have a lot of neurons that crisscross. So they use that, but they use 1,000 of that, okay, to create input-output similar to humans. Okay? That's what they try to do in the 60s. They said it up to my year. Now, nowadays, you try to find intelligent solution, but the solution that you use is based on those functions. So that's why sometimes they call it artificial intelligence, AI driven. It's not really AI driven. It's driven by functions created during AI research. That makes sense? Yeah. But then there's of course things like object visual recognition that's very close to AI experience. But when I say this, I mean finding good solutions. But the function that you used it was created in the 50s, 60s, 70s, 80s, because they were trying to mimic human brain. So sometimes they call it AI powered. Now, I just want to give you a little bit, we almost run out of time. I don't know about you, but I love the math, obviously, but I also love the history of it. There's always a reason when you look back in historical context why things have been written. You know, this breakthrough in AI, this visual recognition, you know, the mathematics was already pretty much done after a graduate, after I got my Ph.D., but certainly not recently. However, because that little thing here, one is not enough. Two is not enough. You need 10,000. And 10,000 of them means you have to do what the computer does. Computer does sequential calculation. So calculate one of these, 10,000 times. Okay? That's what a CPU does. I had very good CPU, well, not very good. I had decent CPU when I was already. And that's what I had. What happened is, sometime after my PhD, maybe 10 years after my PhD, a company got into gaming, NVIDIA got into gaming. Now, gaming in 3D involves visualize 3D, right? Well, to make a long story short, to make this point, which is in 3D space, move to that point in 3D space, is matrix multiplication. Yeah? The point is that for a game scene, the multiplication is easy, but there are so many points in a game that you have to multiply. So instead of having a computer that's acting really fast, they have computers that parallelize multiplication. And that's what this little guy does. This is the game card. It's called GPU, Graphical Processing Unit. It does multiplication there, except it does it in tiny little threads in parallel. What it does is it allows the game scene to evolve. So a game scene is defined by 1,000 points that has to multiply by a matrix every microsecond. So that's what comes. Now it turns out that this multiplication can be adapted so that instead of multiplying this sigmoid 1,000 times in a sequence, I parallelize. Okay? And the computer scientist bought maybe a game card from his son or something like that, and played with it and parallelize. This happened in 2008. Anyway, the breakthrough came out in 2010. And that's the reason why we have that detection, dog detection. And the mathematics was derived, I think, by Professor Fukushima in the 70s. But he didn't get famous for it because he had the mathematics on neurocognition. That came after looking at cats. But until the Canadian group of researchers used basically game board, not game card, to play with it, has a breakthrough. And now we have dedicated card just for that. Okay. And also this card is good for Bitcoin mining. So you got three people, you got gamer, Bitcoin miner, data scientist, fighting for supply of NVIDIA game card at one point. Now it's better. I used to have problems getting access to them. Okay. So that exactly happened. So you can say the story is so beautiful. It starts from cat research in 1968. Again, back then people didn't feel so bad about the cat's brain. But it starts with cat, eventually mathematical model, eventually game card, eventually the breakthrough. And now we can do visual recognition with different kind of mapping. It becomes recognition of text, recognition of borders, recognition of spatial relation, recognition of network connectivity. This thing just blew up. This thing blew up. Okay. Now things still takes a long time. Right? The guy who had the breakthrough in 2011, I think he's the NVIDIA 5 something series and ran for like 6 days or something. Okay. Now we have the latest language model in Thailand, the Thai language model. That requires about maybe 12 times of what I've got here, running for 8 months, and compute a language model. So yeah, things get quicker, but sometimes it takes a long time. Remember I told you that the expected thing is the learning time. And this language model was built at next in Rayong. This was a research center, and they got a million and a half baht worth of computer running for 8 months, and they compute this kind of recognition. So once it's learned, now they will call it. Okay, so once it's built an F, I can give it X and immediately get a Y. Very cheap. Because this was a research institution, they make it publicly available, and in fact, it can go. And that's where you would use Python, because this thing, the interface, if the interface, I think it's in Python and some other language, but I think Python is more important. Because the interface is in Python. If you want to use this, you have to use Python. There's no mathematical interface. So out of luck. So in that case, yeah. Same thing with quantum computing, by the way. With quantum computer, there's a Python code that runs a simulator and all that stuff. It's a bit like English language. Okay? Nobody says English language is the most beautiful language in the world, but it is the most useful because everybody comes to the common platform, right? So yeah, think about it. English language can you can say even clumsy in spelling and all kind of legacy and stuff. It's a bit rule-based, but not completely rule-based. But why does everybody have to put up with all the silliness of English language? It's because a French paper gets translated to English. A Czech paper gets translated to English. Chinese paper gets translated to English. So by learning English, you can read papers from French, German, Egyptian, Cameroonian. It's that thing. So that's why if you're going to apply digital intelligence, you have to put up with Python. And just like if you want to operate internationally, you have to put up with Python. Good. So that's that. Now, I won't keep any. There's nothing to. I was going to give you a sort of assignment to pick up from mathematics, but let me sort out what happens with software. Okay, but do come if it's installed, come with it. I want you to actually play in class. Okay, so there'll be a bit of that, and then there'll be some also on Python exercise that will be later in the class. This is to like get you into the feeling of what it means that you have to create environment for this library, for that library. Okay, very good. So that's it. That's it for today. And again, don't be late. Very important. Oh yeah. Yeah. Why don't you do, before you leave the store and check attendance? I'm not signing. Look. Just leave here, but you have to sign it on your head. Yeah. So you guys are not you're Basai or not Basai?
Yeah.
But okay. But these are not engineering. From engineering school. ISC. Oh, okay. ISC.อะไรนะ International School of Engineering แล้ว specialization อะไรแล้วได้ AI โอเคโอ้ยิ่งดีใหญ่เลยโรบอติกดีมากเลยนะเวลามาทำอะไรกันแล้วก็ by the way make friends with Basai people to maybe yeah excellent โอเคครับคิดแล้วดีค่ะสวัสดีครับสวัสดีครับ